From the St. Francis Yacht Club in San Francisco, this is the Wednesday Yachting Luncheon, hosted by Ron Young.
Welcome to the Wednesday Yachting Luncheon, live from the virtual grill room of the St. Francis Yacht Club. So any of us who've sailed in the ocean and everybody who's surfed ponders, what is this thing about rogue waves? If you've gone to Mavericks to look at the giant wave contest, you are impressed with these 60-footers and wonder, why do they form here? Why do they form at some places out in oceans next to atolls? And what limits the size of these waves? And why do they break? Our speaker today can address this subject as he's an academic who has spent a career studying this very topic. What limits the size of gigantic rogue waves and why do they break? Francesco Fedele is an associate professor of civil and environmental engineering at Georgia Institute of Technology in Atlanta, Georgia. His research spans nonlinear wave mechanics, fluid mechanics, probability and random fields, and all sorts of scientific and mathematical measures about the formation, size, and limitation of these giant rogue waves. So it's fascinating to put the practical experience that some of us have had next to the scientific research and thoughtful work of Professor Fedele. So Francesco, welcome.
It's an honor to be here. Thank you for inviting me.
I noticed that you're a multifaceted guy. I know from talking to you already that you have a very sort of incredible analytic nature, but you're also artistic and expressive. And I noticed that in the Picasso-like figure, you have shaved one side of your face and not the other side of your face.
I've been practicing art for the last 7 years. So I like to paint and draw, and recently I've been involved with choreographers and multimedia artists, and this concept is about dichotomy of the self. Is a performance that I'm preparing for next spring at Georgia Tech. It's about the inner self versus the societal mask. And about self-acceptance, asymmetries, and so on. In 2016, I never did art before that, and suddenly, I wanted to start to draw and paint, and Picasso was the because Picasso with the Cubism is all about geometry, and so being an engineer, that was very easy for me to appreciate and understand it. And then from there I moved to the French Impressionism, with Matisse, Monet, and then I study all history of the arts, and all the artists from the caveman until Bensky. So ocean waves, I'm interested in studying extreme waves, why they occur and how they occur, what is the mystery and physics behind them, and so on. And everything started in 1995 in the North Sea. Here in the North Sea, there are several oil platforms. This is the location of the Draupner platform, where in 1995, on the beginning of the year, on January 1st, this platform, they got hit by a very large wave.
Oil platform in the North Sea.
Yes. At that time, they were doing repairs under the deck of the platform, and there were scaffoldings. The day after, the crew, they didn't see any scaffolding. All the scaffolding was washed out. And then they realized that they were hit by a large wave. Indeed, they went and looked at the measurements, and they found this really very rare extreme wave. It's very interesting that the platform didn't feel anything. Oil platforms are very well designed, and they can endure extreme stresses. And another one was observed later. In 2007 is the Andrea rogue waves, which is still another platform nearby here, the Ecofist platform. And as you can see here, this is the profiles of the waves. They are really very sharp and tall. Let me give you the characteristic. These are the three famous rogue waves. Another one was observed in Ireland. This is the Killard rogue wave. For example, the crest height, which is basically from the mean sea level to the top of the crest. We're talking about 18 meters, 16 meters of height. So these are like water walls.
Meters is a European metric term. And when people look at 15 meters, we're saying 47 feet.
Oh, yeah.
23 meters, we're saying 70 feet. Wave
Yes.
height, 70 feet. Okay. Over to the right there, the killer, that says 25, 26 meters. So we're talking 83 feet. Just
Yes.
look at
And I want you to know, this is the typical period, the wave period of these waves, is on the order of 15 seconds. So that's how the wave grows and decay during this time. So it's a very rapid event. It's very hard to predict, because in such a brief and very intense event.
it looks like shallow water in all three.
Intermediate waters. So
Okay.
Since then, there have been a debate about what is the physical mechanism that generates this large wave in the ocean. And there have been two schools of thoughts. One, which many people follow it, is about the modulation instability and the nonlinear Schrödinger equation, which has been, pioneered by Osborne, Honorato, and Janssen. Some other small group, that which includes me, that I didn't believe in this mechanism, and eventually then I showed that actually these rogue waves are simply linear focusing enhanced by bound nonlinearities. The NLS ocean. So what is an NLS ocean? This theory is only valid for waves that are traveling unidirectionally, like in a wave tank, like the one that you are seeing here. So energy is basically trapped between two walls. Energy cannot spread directionally. And so waves, they can only go in one direction. And so what happened, all this energy, it is basically localized between these two tiny narrow walls, and energy can accumulate and very, very large waves can occur. But remember, this is the ocean between, it's like, if you squeeze an open ocean between two walls, okay? You can imagine how much energy you can concentrate. And so what happened that in this situation, in this scenario, which I call the NLS ocean, rogue waves are typical event of a spatial population of waves, because the system is very spatial, is very particular. Is waves that can only go along one direction.
What does NLS stand for?
Nonlinear Schrödinger equation.
Linear
Schrödinger equation, which is the key equation that model unidirectional waves, but is an approximation because it does not account for breaking.
Are you saying the funneling effect in the North Sea between Norway and the northern tip?
No, there is open ocean. There is no, even if it looks like a narrow gap, the waves, they are very, very short in length. And so there is open ocean. Directional scenario, it is very idealistic. So in open ocean, the energy can spread directionally because now waves are only going in one direction. What happens is that one wave in the middle can steal energy from the neighboring waves and grow at their own expenses. Process repeat cyclically. So you have basically a breeding of waves that grow and decay, because energy is trapped in this long, infinite channel. And so that's the only things they can do. However, this is a theoretical model because it does not account for breaking. So there is an energy limiter. Gravity is working against this huge concentration of energy. And so eventually, the wave can reach a certain height and then it will break.
What you're saying is in this theoretical model, the idea is that the rogue wave basically borrows or steals energy from the nearby waves. That's why they become lower and reduced in size. And as the wave energy from them is transferred to the big giant wave. In this theoretical model, when there is a big wave, it should be preceded and immediately followed by a lesser wave.
Remember that this is true in unidirectional waves. Open ocean is not unidirectional. Do the simulations of an NLS ocean. This is a unidirectional wave and this is time. So this is a space-time view. You can see that, you have all these very recurrent large waves, which are very typical in this ocean. And you don't want to swim here. It's very bad. So, the truth of the matter is that the ocean is open ocean. There are no walls that confine the energy And so energy can spread directionally. And so what happened that all this effect that I was talking about, that when you have three waves and the two neighboring waves, they can squeeze and have all these energy exchanges, they don't happen in the ocean. It's a different mechanism. Indeed, in open ocean, rogue waves are simply rare events of a normal population of waves. How can you use this model of unidirectional channel waves to basically understand the property of what happened in open ocean? So there is some mathematics behind. I was able to study and try to understand these energy exchanges between waves. In 2015, I basically showed that when you are in open ocean, all this modulation instability effect, they are not important. They don't occur because basically energy can spread directionally everywhere. And so these things don't.
Is that an actual photograph? Is that a photograph on the left?
Photograph. It's a photo, actually.
That's actually a photo.
Yes.
Holy moly.
Yeah. It's a very nice breaking wave that maybe, they, for the angle that they caught, looks like this monster. But, eventually, rogue waves may be simple after all. And to me, it's basically the God fortune playing dice with the ocean I want to show. Indeed, what happened is that these physicists, this group of researchers, they're trying to explain a phenomenon that occur in open ocean using a simple theory of waves that they're all unidirectional. Why they're doing that? Because the mathematics, it's easy. There is this very elegant nonlinear Schrödinger equation that has been studied for a long time. So everything is nice and clean. So they can write papers and get fundings and so on. But in 2016, if you remember, there was the discovery of the gravitational waves. I published this work in 2016 in which we prove that real-world ocean rock waves explained without the modulation instability that I already explained you based on the nonlinear Schrödinger equation. So we didn't we look for the keys where we think we lost them and not near the immediate light, which it's easy. And indeed, then I did, these funny rock waves are like your car keys. Don't walk away to the nearest street light because you will not find them. Or then, this other one, lost your car keys, that's rogue. So, and, but actually, let me tell you what I believe is happening, when you are in open ocean, okay? What is the physical mechanism that can generate a rogue wave? First of all is the constructive interference, or what is called linear focusing. You are in this open ocean, waves comes from multiple directions. Eventually, in order to form a large wave, what happened, all this combination of waves coming in from all directions, they basically form a very well-defined physical entity, which is called the wave group. This wave group, is evolving in this direction. It has a 3D structure. It reaches a maximum, and then it will decay. So, that's basically, the linear focusing. You also have to account for non-linearity of the ocean waves. What are these non-linearities? We usually think that waves are sinusoidal. You see, with the crest amplitude equal to the trough amplitude. In reality, if you observe waves in open ocean or at the beach, you will see that they have a sharper crest and shallower troughs. This is a second order nonlinear effect, which is very important because crest trough asymmetry can give you an increase of the crest height from 10 to 15%. So if you combine the sharpness of the crest with the linear focusing or constructive interference that generate wave groups, we were able to explain the occurrence of the rogue waves in the North Sea, Draupner, Andrea, and the other rogue waves.
So
you can clearly see these are simulations of the three rogue waves. For example, these are the simulation we did. This is the probability of the crest exceedance for the Andrea rogue wave. Let me tell you what is this chart. On the vertical axis, you have a normalized crest amplitude which is basically normalized by what is called the significant wave height, which is a measure of the energy of the sea state. And on the horizontal axis, you have the number of waves, okay? So for example, now using linear focusing theory and second order nonlinearities, I developed together with my colleague Typhoon a theoretical model to predict. If you want to know how long do you have to wait to encounter a wave that is going to be larger than 14 meters, you go down, you enter in this diagram like this.
That's like 5 stories for the typical person.
Yes, exactly. Yeah. And then you go down here and you say, okay, every 100,000 waves, say the probability to encounter a wave that is larger than a 5-story building is going to be 1 wave out of 100,000 waves. But when they happen, I mean, they can create a lot of problem, especially for small boats. This is just a simple estimate. And actually, this relates to an interesting theoretical problem. So basically what happens, if you wait long enough in the ocean, in open ocean, you will encounter a very large wave, okay? This is related to the infinite monkey problem, the Borg's experiment, which was mentioned by the theoretical physicist Giorgio Parisi last year when he got the Nobel Prize. He basically, in his interview, because he works on complex systems, and so he basically, I got curious about this problem that he discussed. So what is it? Imagine that you have a monkey that is hitting keys at random of a typewriter. He can type for an infinite amount of time, okay? If you ask yourself, what is the probability that the monkey will type the word rog? Well, I mean, if you wait long enough, so for example, if he's going to type more than 10 gigas of letters, eventually, the word rog will appear. And this is the same this is the equivalent of rog waves. If you wait long enough, you will encounter a rog wave in the ocean, especially if you are also moving space and time. Let me tell you, and this relates to what you explained to me before, your experience, of your encounter rog wave. What happened is that most of the measurements about predicting rog waves, they're basically point measurements, from buoys. You are basically assuming you are at this point in the ocean, and it's a fixed point, and you ask yourself, how long I have to wait for a rog wave to hit me? Well, I already showed you before, you need to wait for 100,000 waves. If you are able to wait enough to experience 100,000 wave, then one of them is very likely to be rog. Why is like that? Because the occurrence of a large wave, it is due to the evolution of a well-defined wave group, which evolved in space and time, and at a certain time, it will get its maximum height at this point, and then it will decay. However, the chances that your buoy or this fixed observer to be hit by this large wave at this focusing point is that the probability is basically 0. The fixed observer will mostly observe, will feel the tail of the group. If you are a surfer, have you ever seen a surfer that waits at one point of the ocean for the large waves to come? Not really. What the surfer does, he moves around an area, and the chances to encounter a rog wave, they increase. So this is what I studied. In order to validate this theory, in 2007, I did my first experiment at Georgia in Venice. It was my first project at Georgia Tech. I got funded by Chevron. And I basically, in Venice, there is a tower, which is called the Acqua Alta Tower, on which we installed the stereo cameras, and we were able to, that's the location. It was still in deep water. Okay? We were able to, from these 2 cameras, we were able to reconstruct the surface fluctuations in space and time. I was able to validate the theory of space-time extremes. So here you can see some, at that time, with this space-time data, you can do all these very interesting, colorful plots. This is what I call the space-time volume. This is the Y and X area that we image, and then is the time evolution. You can represent the surface motion in this diagram like this.
So red is tall and the peak crest, and the blue is the trough.
Yes, exactly. Very good.
Okay.
Yes, exactly. But now let me tell you what is going on. Let me tell you the state of the art analytical models for rogue waves. Until 5 years ago, that was the model I was talking about before, the nonlinear Schrödinger equation, which is also a very famous equation in quantum mechanics. So this is only for waves in one direction. In this model, there is no breaking. Waves can grow as much as you like. However, if you account for the effect of breaking, this is the latest model. And I just want to show you the math. So basically, this is just a limitation. This is good, when you want to study tiny small waves. But when the waves start to become agitated and more intense, it is not enough. You need more terms which model for the breaking. Okay, show you this equation to show that the mathematics is very intricate. But let me just tell you, in simple word, what happened with breaking. So a wave has a certain energy. Each point on this diagram represent, if I look at this point here, it represents the energy of the wave and the correspondent phase speed, how fast the wave travels through ocean, okay? And so what happened, as the wave become larger and larger, the energy increases, okay? And they go faster and faster. They reach a limit. There is a point above which the energy cannot grow anymore. Okay. And then it bends down, okay? Huh. And that's basically the breaking mechanism. This is the slowdown effect. As the wave grows in amplitude, kinetic energy is converted in potential energy. And when they do that, they tend to slow down. But then what happens, when the wave becomes steeper and steeper, they become less dispersive. And then what does it mean? It means that this slowing down reduces until to the point that the wave cannot anymore accumulate more potential energy, and then it breaks. And all the energy will go in kinetic energy with the formation of these huge jets and spilling.
You're saying even in a windless, no wind environment, because usually it looks like the wave crests, the top of the waves get blown off. Their hats get blown off the waves, which is what the white caps on the top look like. But what you're saying is even if you had a wave that height growing just like, but with no wind, you're saying the wave crest would slow as it gets taller. And secondly, you're saying there would be circumstances under which it would break, even though the wind is not blowing the top off.
Yes, exactly. The wave is like a storage, which can accumulate energy that comes from the environment. But, this storage is not unlimited. And then once you reach that storage capacity, eventually all the excess energy will go in the formation of these jets and breaking. This is the state-of-the-art research up to now when it comes to breaking, trying to validate these results using theory and experiments.
So why is the forward face steeper after a back of the wave?
You see that here the back is less steep than the front, but this is very long wave, and so it travels faster than this tiny wave here. So eventually you see that it will catch up and become symmetric, and then the reverse will occur. It is related to the natural dispersive nature of waves. This is very similar. Now, if you look at when you're riding on a boat along a channel, along a river, if you pay attention, you will see that the longer waves will be the first one to arrive at the borders. And the shorter waves, they're the one that will come later. Gravity acting on waves that make them to behave dispersively. Try to understand the breaking mechanism. I was talking before about the wave group. Actually, you can think of the wave group like a cat or a dancer. Indeed, if you think about the dancer, because it conserves angular momentum, she can basically change the speed of rotation by simply changing the shape of her body. If enlarge the hands, she will slow down. If she basically put the hand down, she will speed up.
Well, but what she's really doing is she's taking the angular energy in her arms and bringing it inside of her body. So she's not dragging her arm out there leverage wise, right?
Yes, it is conservation of energy. The same things with the ocean. There is conservation of linear momentum. So, and basically the waves, by changing their shape, they can accelerate and decelerate. Okay, like a dancer can speed up or slow down.
Okay,
This is an important physical, I believe this is the key concept that contain the physics of braking. So, and that's what I'm trying to investigate with some collaborators in Italy. And indeed, but mathematically, what I was very impressed, when we were studying the mathematical models of these ocean wave groups, what is interesting that, you look at these beautiful plots. This comes from the physics of wave groups, plus some mathematics, which are called toric groups orbits. And they're very artistic. Look at this. This comes from mathematics. When you say that mathematics is the highest form of art, basically, I just want to show you these plots and introduce that besides doing waves, rock waves research, over the last 6 years at Georgia Tech, I try to infuse art into the curriculum.
So you got Botticelli, you got Modigliani at the bottom.
Yes.
Yeah.
Picasso. This is Renoir. This is Renoir, Modigliani, Picasso. This is the Virgin of the Rocks of Leonardo. This is Michelangelo, the Creation. Yeah. And this is Botticelli, and this is Giotto, San Francis. So I gave, you see all the
credit.
And of course here you have the brain waves, the brain art to try to, that's I'm glad you like that. So it's very interesting because I created this special topics course, visual arts and geometry, in which I teach students the foundation of geometry that allow Einstein to formulate his spatial and general relativity. And then I also took together with the help of an artist. This is a course that is co-taught with an artist and myself. The artist teaches students fundamentals of drawing and painting, because actually, if you modern science is Einstein and modern art is Picasso. They were contemporary in the 1900s. Actually, Picasso was influenced by the geometry concept. They were important also for Einstein to formulate the special relativity. And indeed, this is the famous painting by Picasso in 1907, the Mademoiselle d'Avignon, which is basically the beginning of modern art, in which you can see that he was so influenced by decided to use the language of geometry to express the reality surrounding him. And, this painting, what is interesting, besides, you can see that he used masks. He was fascinated with African art and African masks.
So when he first saw the African mask, he began to see, as you turn the mask in different images of it, the old saying, or something I say, where you stand has a lot to do with where you sit. As you change your perspective, you can get new insights into
exactly. And that's the point of the cubism, because the key element on the novelty of this painting is this lady. These are basically, Le Mademoiselle d'Avignon. There are 5, is a bordello in Avignon that he used to go when he was young, and he basically painted, the 5 ladies working there. And the squatting lady, that's the key, because here you see the back of the lady, but then you can also see the face. Mm-hmm. And you see the front and facial face and side view of the face. So this is basically the concept in geometry of multiple perspective on the same image. And indeed, that's what we do in this course. We teach students to learn how to see, because that's what the art of painting is, to learn how to see. Right. And it's very important to draw from life. And this is one of our spooky still life, we do in October. Then we also did painting from life last year. And so we did oil. And these are drawings by some of the students. I mean, some of them, they had some minimal artistic trainings. Others, the majority never had it. But you can see that, there is this instinct of creating, and, they're still engineers, so they have knowledge of geometry. And so these are very nice, well done. She's one of in 2021, Isabella, she made these beautiful self-portraits, from painting from a mirror. Very well done. I mean, she discovered, that she loved to paint, when she took this class, and now she's basically a full-time artist.
Really?
Yes. And then, because I'm working with rock waves, so I start to be interested on brain waves, try to understand.
An EEG, electroencephalogram, right?
Yes, exactly. So you can use, and they're very cheap now. You can buy these Muse headsets for $200 in Amazon, and you can record the brain waves. And then what we did, similar to what you did with your art performance, we converted how brain waves into music using software that is called Super Collider. And our goal was to understand, does the sound of an equation is different than the sound of making a painting? And here you can see the artist, Rachel Grant, that she teaches the course with me, and myself here. This is my student that helped me with software to convert the brainwave to music. And this is Bella Dorado. She's a dancer and choreographer, very famous here in Atlanta. These are some snapshots. I'm going to show you now the video. And that's... Can you hear the music?
Yes.
So what happened is that, myself and Rachel, we wear the headset. So our brainwaves are converted in music. And then we're just a starting point. Then here I start to write equations. You can hear that the music is very intense. So, here I'm writing equations, are very focused. All my brain is producing conscious waves, mostly beta and alpha. You can see from the background. And basically, the dancer, she's responding to the music. And she's improvising, okay? Nothing, right. We didn't plan anything. So you see the music is very intense, okay? The music reflects my brain activity of writing an equation. And now we switch to Rachel. And now she starts painting. And she's a well-trained artist. And so you can see that the music is more gentle because, she's mostly producing unconscious waves. So when you see that, and then eventually at the end, now the next step, I will start to draw together with Rachel. She paints and I draw. The music is very beautiful, so it's very harmonious. And the choreographer, she's basically improvising. And you go, now the music change. And so now I basically draw. We paint and draw together. So actually now the music, and so you can see now the paintings start to evolve and start to shape in this abstract form. Yes, I'm just making drawing without thinking. So I was trying to basically, try to be as spontaneous as possible, and just draw by imagination. And actually, it's interesting there that I'm drawing this man that is walking over a tiny cable, and so in equilibrium. I don't know, maybe expressing the stability of the mind. And anyway, so and then the last step. The Bella Dorado, she is gonna wear the headset, and she will dance to the music that she produced. So anyway,
So who's wearing the headset right now? Who's
now is in the choreographer, Bella.
Okay.
She's making her own music now.
Got it.
And dancing to her own music. So there is some kind of feedback.
Wow. In the world of amazing coincidences, back in 1969, I created a piece of art using my brain waves, in other words, my EEG and my EKG and my GSR to drive a Moog music synthesizer. And I displayed those three metrics also on a wall, which I saw. And as I saw that wall and I heard the sound that was created, I had reacted to it, which created new visual art and new audio art. This piece of art created a real-time feedback loop between my bioreactions to what I was creating. This piece of art was featured by the San Francisco Art Institute on the front and back cover of their traveling show catalog in 1969 and 70. So what an amazing coincidence that each of us would have played with biofeedback.
How can I measure creativity using brainwaves? What does it mean to be creative? Can creativity be measured? And this is still an open field. And in the same time, these brainwaves, they're waves. So there would be rogue events even there. So, and very likely now, because, is the spiking of the brain activities now is very intense. And yes, basically it. Thank you for having me here, for inviting me.
Great, Francesco. We can't wait till you come back to San Francisco.
I would love to do, yes.
Yeah, we'll have you buy a drink or a dinner at the St. Francis Yacht Club. Let you look out the window at the waves in front of our club and the Golden Gate Bridge, etc. So thanks very much, Francesco Fedele, basically for sharing with us your thesis on rogue waves, how big they can and can't get, and what's different about the theoretical modeling of waves
and the reality.
Waves. And then your real fun adventure talking about correlation between brain waves and musical expression and artistic expression. Real fun talk. Thank you very much. And with that, we adjourn another Wednesday Yachting Luncheon.
Thank you.
Bravo.
Thank you.
This has been a presentation of the Wednesday Yachting Luncheon.